In this next section, we're going to discuss a different type of oscillation that can be modeled as simple harmonic motion, even though it doesn't quite perfectly work out that way. And that is the motion of a pendulum. We talked about pendulums when we did Lab 102 earlier in the semester. So a pendulum has an equilibrium position, which is essentially vertical, and you pull it back some angle theta away from the equilibrium, and it's going to swing back. So the pendulum has a length, pendulum ball has a mass. So the force here that is going to restore this to its original position is the force of gravity in the x direction. So we have a force of tension here, force of gravity in the y here. So because theta is opposite to this, we're going to use sine. So we're going to find that our restoring force is equal to mg sine of theta. We're going to assume a small angle here, and I'll show you at the end of this section what the consequence of assuming a small angle does to our calculations. Alright, once again we're going to go back to the idea that S equals R theta. S being the arc length, R being our distance from the point of rotation, and theta of course being the angle it sweeps out. So we're actually going to end up replacing this with S equals L theta. So in this equation, S is very similar to the x, or distance from equilibrium, that we used in the spring force relationship. While everything else in the equation describes the pendulum itself very similar to K describing the springiness of the spring. So we're going to do sort of a hand-waving derivation here. We know that angular frequency is equal to the square root of K over M, and we're going to say this is very similar to the idea of mg over L divided by then mass. And this is going to equal then G over L, so the mass ends up canceling out. So we know period is equal to 2 pi over the angular frequency, since it's going to be the inverse of your regular frequency. And that's going to equal 2 pi times the square root of L over G, or the inverse of what we saw up here. So the period of a pendulum is equal to 2 pi times the square root of L over G, where L is the length of the pendulum string and G is the acceleration due to gravity. So be careful here, we learned in the prior chapter different ways to calculate the acceleration due to gravity, so we might not use 9.8 in these types of problems. And T is the time for one oscillation, so the swing out and then the swing back. So remember, this is for small angles only. Alright, so I want to show you what the simulation is. If I pull this back 5 degrees and let it go, so I'm going to start timing it here. So our time for one oscillation here is 1.85 seconds, so remember that number. I'm going to take this now and I'm going to pull it back to 70 degrees and let it go. Alright, let's see if I can start it. Alright, so pushing this on the screen is a little bit hard. So you can see it's over 2 seconds. So there is a difference between if you pull it back only 10 degrees and if you pull it back a much higher angle. So be careful to remember that this is a small angle approximation, or else you may run into issues with calculations.